about our assigned topic, which is the mathematics of graph.
Are you ready to dive into something new?
But before we formally start our discussion, let us introduce ourselves first. So I am Marlon Marsubong.
And I am Joshua Gilimbago.
My name is Giselle P. Velasco.
And I am Nino Angelo A. Mora.
And we are Team 8!
Now, let's begin with our topic. Unit 2 for Mathematics of
Graph.
To start this discussion, we have to comply these learning objectives, define what is graph theory, and determine the edges, vertices, order, size, degree vertices, and degree sequence of a graph. Identify the adjacent and incident on vertices and edges of a graph. Construct different types of graphs and distinguish the difference between a bipartite and a complete bipartite graph. Find the complements of a single graph and complete bipartite graph. We have to differentiate walk, trail, path, circuit, and cycle, and show that the two given graphs are isomorphic and whether a graph is a planar or a non-planar. We have also to use Euler's formula to determine planarity of a graph, determine whether a graph is Eulerian, semi-Eulerian, and non-Eulerian. But, especially, we have to explore the applications of graphs. To start this, our table of contents, we have this Unit 1 basic concepts, graphs and Euler's formula, weighted graphs, Euler's formula, and lastly, the graph coloring. As first, what are the basic concepts in the mathematics of graphs? Let me ask you everyone, what is graph theory? Are you familiar with this word graph theory? If not, a branch of mathematics. A graph theory is a branch kuno sa mathematics that concerned with networks of points connected by lines. It is defined as the study of graphs and its mathematical structures, used to model pairwise relations between objects from a certain collection. It was started in recreational math problems, but it has grown into a significant area of mathematics with application in different fields. For example, in computer science, it is used to represent networks of communication, data organization, computational devices, the flow of computational, and others. For example, the link structure of a certain website, which could be represented by a directed graph. The web pages at the website are what we called the vertices, and a directed edge from page X to page Y exists if and only page X contains a link to page Y. It is also useful in social science, chemistry, operation research, and in other fields. We have a graph G consists of non-empty finite set of vertex set of graph of elements called vertices, or the nodes, and a finite edge of the graph of unordered pairs not necessarily distinct called edges, or the edge family. The vertex set is denoted as V open parenthesis G and close parenthesis. The edge set is denoted as edge E open parenthesis G close parenthesis of the graph, denoted by V open parenthesis G and close parenthesis. This is for vertex or vertices. And for the edge, it is denoted by E open parenthesis G and close parenthesis. And this is the edge or the edges. And we have 3 examples for a graph, and we will find what are the vertices and the edges of these 3 graphs. Example number 1, we have this vertex A, vertex B, vertex C, and the vertex D. To know what are the vertices of a graph, we have to look for the points or the dots in the graph. To look for the edge, we will look for the edge A to B, A to C, B to C, and C to D. So we will write first the vertex, V, open parenthesis, G, and close parenthesis is equal to, we have this vertex A, B, C, and D, and don't forget the parenthesis. And then for the edge, we have this E, open parenthesis of G, close parenthesis, and we have this line segment AB, AC, BC, and CD. So we have now the vertices and the edges of the example number 1. So next example, we have this vertex A, B, C, and D. To write this down, we have this edge AB, BC, and CD. For the vertices, we have A, B, C, and D. For this number 3, we have this vertex A, vertex B, vertex C, and the vertex E. So vertex is equal to A, B, C, and E. And for the edge is equal to AB, BC, and PE. Already identified what are the vertices and the edges of the graphs, and now we will dive in what are the order of the graph and the size of the graph. First, we will know what is order of the graph. It is the number of vertices. So remember that order of the graph is the number of vertices in a graph. And the size means it is determined by counting the number of edges. Remember, counting the edges in a graph. In an order of the graph, we have to determine and count the number of vertices. While in the size, it is by counting the edges. We have to draw a graph like this. And we will put a point here, a dots, in each sides. This is vertex U, V, Y, X, and Z. We will figure out what are the vertices and the edges of this graph. So we have this V, open parenthesis, G. We have U, V, X, Y, and Z. These are our vertices in this graph. And for the edges, we have UV, VX, XZ, YZ, UY, VY, UZ, and VZ. So we have 8 edges. These are UV, VX, XZ, YZ, UY, VY, UZ, and this line segment VZ. This, one, this, and this one. So we have 1, 2, 3, 4, 5, 6, 7, 8. And the order, there is 1, 2, 3, 4, 5. So our order in a graph is equals to 5. And the size equal to 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 sides in. After determining and finding the edges, the vertices, the order of the graph, and the size, we will go to the adjacent or the neighbors of the graph. It is if 2 vertices of graph G has an edge joining them, and the edge joining them is called an incident. We have this example. We have this vertex A, vertex B, vertex C, and vertex E. In this, we have this incident, this X. This is connected to the 2 vertices that are points connecting to the edge. So this is our incident. For the adjacent, B. We will look for the adjacent of B. B is adjacent to A. And B is adjacent also to vertex C, and B adjacent to vertex E. B has 3 adjacent vertices. These are A vertex, vertex C, and vertex E. We will also look for the adjacent of A. The only adjacent of A is the B, adjacent to vertex B. And our C, vertex C, is adjacent to B and adjacent to E. And lastly, our E is adjacent to C and B. Forget that in this graph, X is incident to A and B. We are done with finding the adjacent and the incident of a graph, and we will go now to multiple edges or the parallel edges. It is a pair of vertices consists of more than one edge, while an edge whose endpoints are the same vertex is called loop. Ang edge kuno pareha ra siya og endpoints, gitawag ni siya natog loop. Unya ang graph na walay loops, it is called loop free. For example, in this graph we have vertex A, B, C, D, and E. In this graph we have edge AC with a multiple edges. This is what we call multiple edges. While the vertex D is what we call contains a loop. This vertex D contains a loop, and loop looks like this, like a ring. And the other important terms is the degree in graph. We have the important degree. We don't have to forget the degree in our graph, because the degree of a vertex of graph G is the number of edges incident with the vertex noted as dig 1. This is how we note our vertex, the degree. In this graph, the degree of the vertices A, B, C, D, and E of graph G are 3, 4, 4, 4, and 1 respectively. For example, the degree of A is equals to 3. Why? Because the edges B, A, B, C, B, D. And I'm so sorry. A is A to B, and this what we call the multiple edges. That's why it is equals to 3. And so the degree of B is equals to, we have these edges of BA, BC, BD, and BE. So it is equals to 4. And the degree of C is equals to 4 also, because we have this loop and the CB and the CD. And for the degree of D, we have also 4. Why? Because DB, DC, that's why it is 4. And this last is degree of 1 is equals of E is equals to 1. Why? Because it has only one edge, this edge A, E, and E to B. Take note that a vertex with loop has a degree of 2. Okay? So, ngano siya nahimong 4, kay si degree ng vertex nga loop, nga naay loop, kay equivalent of 2 na siya ngano, imo siyang i-add sa pila iyang edge. And then, we have this, the graph's degree sequence. Graph sequence, or the degree sequence. The degree sequence of the graph. The graph degree sequence was arranged in ascending order. When we talk about ascending order, ato ni siyang i-arrange sa gamay to dako. So mahitabuan ni, sa mahitabuan ning 5, mahimo ni siyang degree sequence is equals to 1, 3, 4, 4, 4. Mao ni siyang mahitabuan na. And then, in addition, the degree sequence of graph G consists of the degrees written in increasing order with repeats are necessary noted. Kaya dapat siya, appeal siya sa tanan nga, imuha siyang i-represent as a degree of this graph. Sabot to ta? We have also this vertex nga wala siya na belong sa tanan nga any edge, and ang iyang degree is 0 ra jud siya. And this is what we called isolated. This is a vertex is considered as isolated if it does not belong to any edge and has a degree of 0, while an end vertex or the pendant is a vertex with degree of 1. For this example, we have this vertex A, vertex B, vertex C, vertex D, and vertex E. Kaning graph, we have this one isolated vertex, which is this vertex E. Wala siya kay wala siya yung edge nga makasumpay bisag kinsa ani nga mga edge, kaya gitawag siya og isolated, kaya inusara ra siya, wala siya line nga nagka-connect sa uban nga mga vertices, kaya mao ni siya kay nalayo ni siya sa ubang mga vertices nga nag-connect to each other. Theorem 10.1. In a graph G, the sum of the degrees of all vertices is twice the number of edges. For corollary 10.1, the sum of the degrees of the vertices of a graph is an even number. And last, corollary 10.2, in a graph G, the number of odd degrees is even. To verify Theorem 10.1, Corollary 10.1, and 10.2, by example, let us consider the graph in Figure 4. The sum of the degree vertices of the graph is 1 plus 3 plus 4 plus 4 plus 4 is equals to 16. The number of edges is equals to 8, and degree of E is equals to 1. Thus, the number of odd degrees is even. Theorem 10.1, Corollary 10.1, and 10.2 hold based from the graph of Figure 10.5.
Now let us proceed to graphs and Euler's circuit. And now we will tackle about the types of graph. First is the simple graph. A simple graph consists of a non-empty set, non-empty finite set, vertex of graph G of elements, and a finite set, edge of graph G of distinct unordered pairs of distinct elements, vertex of graph G. Meaning, it is a graph with no loop and no multiple edges.
So natay duha ka example nga graph ani. So karon nato silang atong pangitawan og asa nilang duha ang simple graph. So ari natunan sa graph A. Ito na siya i-consider sa graph A. So ani, nagka-connect siya, nay edge, nay kuan, but nakita nato nga nay na siya loop. So simply i-cancel nato kay dili siya ang simple graph. So ani sa graph B, makita nato nga ag A to B isa ka edge, and B to C, tas C to E, and E to D, tas back to D to A. So makita na to nga dili multiple yung edges. So wala siya loop. So simply mao ni ang kuan simple graph na itong ipakita.
The second one is the multigraph. A multigraph is a graph which consists of a vertex of graph G and edge of graph G, except that E contains multiple edges.
We have here an example of a graph with multiple edges, or so what we call as multigraph. So unsa man nakapamultigraph niya? So ang nakapamultigraph niya is kani siya kay kanang edge ni D or A and E, kaduha ni balik. Kaduha which is two edges. Mo man nakapamultigraph niya. Mo multigraph siya.
Next is the pseudograph. It is a graph with at least one loop. The graphs in Figure 10.12 and Figure 10.13 are pseudographs. A trivial graph is a graph with one vertex and no edge. Figure 10.14 illustrates a trivial graph.
As mentioned nako, si figure 10.12 and figure 10.13 mo ni sila ang example sa pseudograph. So maguna ta sa 10.13. Anong gitawag man siya nga example sa pseudograph? Kay as mentioned sa meaning sa pseudograph, a pseudograph is consists of at least one loop. Tapos makita mo nato nga nay one loop which is a vertex D. Manang matawag nato siya nga pseudograph. Ani proceed ni 10.12 which is 10.12. Ani, kita pa nato nga nay loop si vertex C. Tapos basin matinga mo nganong gitawag ni siya nga one loop. Bisag duha ka circle lang nagpa-circle ni vertex C. Gitawag ni siya ay more gi-consider ni siya as one loop. Kaya naraman sa isa ka vertex siya ga loop. So, manang isa pa sa example sa pseudograph. And naputay isang gitawag nga trivial graph nga naginusara ra jud siya like one vertex, no edges, wala like isa ra jud siya ka point, like just a point. So mo ni siya ang example sa trivial graph.
And the next is the regular graph. A regular graph is a graph in which each vertex has the same degree. If each vertex has degree r, the graph is regular of degree r or r regular.
So, this graph is an example of a regular graph. As regular graph, kay as mentioned sa definition niya, a regular graph is or has the same degrees in all vertices. So, as you can see, the ending of vertex, kapila man siya gi-connect or kapila man yung edge in every sa ubang vertices. Diba? Isa, duha, tulo. And let's tanong na to sa uban tulo ba pod. So, isa, duha, tulo. Isa, duha, tulo. Isa, duha, tulo. So, as you can see, equal sila tanan og degree. Man ang natawag siya as regular graph.
Next is an empty graph. An empty graph has no vertices and no edges. And side by an empty graph is the null graph. It is a graph whose edge set is empty.
So, the next example is here. Kani siya. So, kani siya, matawag na to na siya nga ano yung empty graph. So, as you can see, empty siya kay wala man jud jamoy, wala vertices, no vertex, no edge, and no degree. Ano siya ang empty. Empty. Like kani sila. Mo na example of a null graph. A null graph is it has vertices, multiple vertices, but it doesn't have any edges or degree. So mura po siya like kani siya isa ka buok nga ni. Matawag po ni siya nga null, pero mura po siya ma-consider as trivial. So mura igsuon ra null and trivial. And 0 degree.
A subgraph. A subgraph of graph G is a graph. Each whose vertices belong to vertex of G, and each edge belongs to edge of graph G. Symbolically, a subgraph of graph G is equals to VE is a graph G prime equals V prime E prime, with V subset are equal to V and E subset are equal to E.
So, kani nga graph, mo ni siyang example sa subgraph. And kani, as earlier said, di ba? Mo ni siya ang regular graph. And ang subgraph is part siya sa regular graph or half sa regular graph. Mo na gitawag nga subgraph. Kay subgraph man siya sa regular graph.
After the subgraph is the complete graph. A complete graph is a simple graph in which each pair of distinct vertices is adjacent. There is exactly one edge joining every pair of vertices. It is denoted by k sub n on e n vertices, and it has 1/2 n times n minus 1 edges. A complete graph is a regular graph of degree n minus 1.
So, these three are some examples of a complete graph. So, ano ito yung meaning sa complete graph? A complete graph is a simple graph in which each pair of distinct vertices is adjacent. So, ito may meaning sa adjacent ba yun? Ay, go! So, yung meaning sa adjacent. So, ang meaning sa adjacent is ang vertex nga ni-connect nila. Ni-connect sa dua ka pair of vertices. So, go! Matala na ito mga example. So, this is the first example. Nakita mo din na ito. Asa may adjacent ilan ni pwede kani. So, kaya nga natawag mo siya na kuhaan nga adjacent. Tawag siya adjacent. Kaya kani mo, may nag-connect nila. May nag-connect sa each pair of graph. Kasi ito sa ari kadua. Kani kita mo ni si graph D. Ay mo ito sa so ito yung graph D. Ay, vertex D rather. Connect siya sa each. Connect siya every vertices. So, ano gitawag siya na? Adjacent to it. Ang gitawag siya complete graph. Saan yung matanan na pang anong kani, mabalik siya sa tunga. Ano gitawag siya? As mentioned guys sa definition nga, each pair, so, pwede kani po. Ay mo connect mo. Kung siya mo connect ka every mo sa duha ka dot, which is a pair. Okay. And take note nga, ang complete graph is a regular graph of degree n minus 1.
Next is the cycle graph. A cycle graph is a connected graph that is regular of degree 2. It is denoted by C sub n. On the contrary, a graph with no cycle is acyclic.
So let me provide you some graphs that are cycle graph. These two are basic examples of cycle graph. So, ano sa mean sa cycle graph? So, ang cycle graph is it's a graph that consists of 2 degrees. So, ito tanong 2 degrees pa din siya every vertices. So, kani, let's say na vertex A ni siya, tas B, tas C. So, si A, so pila man nag-degree ni A? Duha. Nga namang duha. Kay, naka-edge siya ni B and na po siya edge ni C. Diba? So, let's proceed to the second example. So, kani, let's propose nga A ni siya, A, tas B, C, tas D. Tara na to, tagduha pa po nag-degree ni example B. As magmakita man jud nga tagduha no. So A connects to B, tas A connects to B. Wala may linya sa tunga sa duha ra jud siya. Natura kasi pulag cycle graph din. Thank you.
After that is the path graph. A path graph is a graph obtained from cycle graph C sub n by removing an edge on n vertices denoted by P sub n. And side by side by path graph is a wheel graph. A wheel graph is a graph obtained from C sub n minus 1 by joining each vertex to a new vertex V is the wheel on n vertices denoted by W sub n.
So here is some graphs that is an example of a path graph. And then here is also some graphs that is an example of a wheel graph. First, let us see the examples of a path graph. So as you can see here, a path graph is iko siya gikan sa cycle graph. So kani siya, hintay. Yun is siya nabuo, which is like say nga nangana tas na. Cycle graph na siya. Balik. So remove siya path graph. Of course, this also kani kedua, sa piece of 2. Hintay triangle ni or bisag square. Like may dot are, dog nga na siya. Cycle graph na. Pero kung kuha na ito ng duha ka vertices and duha ka edge. So, ano siya may isunod na path, which makes it a path graph. So, see the wheel graph. So, as you can see here, ang wheel graph is more siya graph nga nay na sa tunga nga vertex to connect every other vertices. Ay pala niyo, ito siya wheel graph kaya siya nasa tuna. Ang nakakunik in every other vertices. May bararyo, nakawheel na ganun siya forma. Kaya naman siya more steering wheel nga graph. So simple as that. That's what it
Platonic graphs. Platonic graphs are graphs which form from the vertices and edges of the five regular Platonic solid: the tetrahedron, octahedron, cube, icosahedron, and the dodecahedron.
So, these are the Platonic graphs. First is the tetrahedron, second is the octahedron, third is the cube, and fourth is the icosahedron, and so on. So, mo ni sila ang Platonic graphs. Ug itanaw kani sila in third person point of view, mga shape ni sila. Kani siya pyramid, kani murag pyramid nga murag mas dagag sides or dagag kanang mga faces. Kani mas mention cube. Mas kare o libo kay siya mga shape kanang dagan kay nga pyramid po siya na triangle. Ano? Atong pangitano pila ka buka faces in each Platonic graphs. Mo ni sila ang FDE, meaning faces, vertices, and edges. So, you know, faces tetrahedron. Ang faces niya is kani. Ato siya tanawon in third person point of view so that we can see the katong every face niya as a shape. Kani, 1, 2, 3, ang nasa tubang is 4. So, ang faces ni tetrahedron is 4. And yung vertices stands for the dots. Oh, so pila may dots niya, vertices. 1, 2, 3, 4. So, 4 yung vertices. Ang edges are the lines that connect each vertices. Oh, 1, 2, 3, 4, 5, 6. So, there are 6 vertices in this Platonic graph. Sa tetrahedron. Ay, 6 edges in the Platonic graph. Let's proceed to octahedron. So, let's first find the faces. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 8 faces for octahedron. And yung vertices are 1, 2, 3, 4, 5, 6. 6. Pwede man mabuhat ang graph. So, 1. And yung last na itong karon is ang iyang edges. Which are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, there are 12 edges in octahedron. And third one is the cube. And so una, ay magbukat ang rumana niya ko. Thank you.
Next to Platonic graph is the bipartite graph. If the vertex set of graph G can be split into two disjoint sets A and B so that each edge of G joins a vertex of A and a vertex of B, then G is a bipartite graph. Alternatively, bipartite graph can be colored black and white vertices.
So mo ni siya ang example sa bipartite graph. Go. So bipartite graph, nagkunti siya og black and white nga vertex. Ang sabi mo. So, but always remember nga a white vertex which is a white nga vertex or dot, if this is adjacent, same sa black, hindi siya adjacent to each other.
Theorem 10.3, a graph G is bipartite if and only if all its cycles have even length. A complete bipartite graph is a bipartite graph in which each vertex in A is joined to each vertex in B by just one edge. It is denoted as capital letter K, R, S with R for black vertices and S for white vertices. Figure 10.25 shows 3 examples of complete bipartite graph. Observed that black vertices are connected with white vertices and there are no multiple edges. Next is a complement of a graph. The complement of a simple graph in which two vertices are adjacent if and only if they are not adjacent in graph G. It is denoted by big letter G. In other words, there is an edge between two vertices U and V if and only if there is no edge between A and in the original graph G. To determine the complement of original and simple graph, we will fill in all the missing edges to get a complete graph, and we will remove all the edges that were already there. Note that it is not the set complement of the graph. Only the edges are complementary. Just like this example, note that the complement of a complete graph is a null graph. The complement of complete bipartite graph is a graph having the following properties. It has no vertex in A or the black vertices, is adjacent to any vertex in B, the white vertices. Every vertex in A is adjacent to every other vertex in A, and every vertex in B is adjacent to every other vertex in B. In this figure, it shows graph Kia and Ka and their complements. Observe that the complement of complete bipartite graphs is not connected. And now we will talk about what is walks, what is trails, paths, circuits, and cycles. Walk in a graph, it is a movement from one vertex to other vertices passing through their edges. Just like for this graph, for example, in this we have A, B, and C, B, C to D, and A, B, C, D. We will write this down as the vertex and the line to edges A to B and B to C. Next, we have B to C and C to D. And now we will go to A to B, B to C, and C to D. And this is how a walk in a graph looks like. For the circuit, it is a walk in a graph that starts and ends on the same vertex. Okay, remember and reminder nga kaning circuit magsugod and magtapos po ni siya sa same ra nga vertex. For example, we have A, B, C, D. And lastly, to A. It ends with A. Okay? For example, we have A to B, A to B, B to C, C to D, and D to A. Next, we have D to E, and E to C, and C to D. Next, from A to B, B to C, C to E, E to D, and D to A. Lastly, we have from B to C, C to E, E to D, D to A, and A ends with letter B. We can see that it starts with vertex A and ends with a vertex A. That's why it is about a walk in a graph that starts and ends with the same vertex, just like this. And we have this Eulerian circuit. In Eulerian circuit, it is a circuit which traverses all edges only once. Remember, it traverses all edges only once. Kas-ara siya mubalik. For example, in this graph, we have from A to B to C, E, D, C, and A. Get? We have this A to B, B to C, C to E, E to D, D to C, and C to A. Again, we have this also from C, vertex C, to vertex E, to vertex D, to vertex C, to vertex A, to vertex B, and to vertex C. Like this. In vertex C, go to vertex E, go to vertex D, go to vertex C again, and go to vertex A, and to B, and lastly to vertex C. We can see that it only traverses all edges at once. Remember, it traverses all the edges of the graph in just one. And then we have this Eulerian circuit theorem. It is a graph. A graph is Eulerian if and only if all vertices of the graph are of even degrees. Just like in these two graphs, we will look for this number 2 graph. We will count if all of these degrees in its vertices are in even degrees. In A, we have A to C, A to B. So it has 2. A is equals to 2. And then for B, it has B to A, B to C. So it also has 2. For C, it has C to D and C to E. It also has 2 degrees. And D is equals to D to C, D to E. 2. And for the E, it has also 2. So this graph is called a Eulerian circuit theorem because it has an even degrees of all of its vertices. But in this graph, A to D, A to B, it has 2. B to A, B to C, it has 2. D, we have, okay, we will start with C is equals to, it has C to D, C to E, 2. D is equals to DA, D to C, and D to E. It has 3 degrees. In E, it has 2 degrees. Because D is in 3 degrees, it is an odd degrees. So this graph is not a Eulerian circuit theorem because remember, not all graphs have the same number of degrees in their vertices. So remember everyone that you have to look for its vertices if it is even because not all are having the same number of degrees. Cycle is a circuit that does not contain any repetition except that the initial vertex and the terminal vertex or the closed path such that A cycle of length k is called a k-cycle. A cycle is called even or odd if it contains an even or odd numbers of edges. It summarizes some important points concerning walks, trails, paths, circuits, and cycles as shown in table 10.2. In walks, the vertices repetition is allowed. In edges, repetition is allowed. Trails, repetition is also allowed. Repetition is not allowed in its edges. In paths, repetition is not allowed except possibly in the initial and terminal vertex. In the edges, repetition is not allowed. In the circuits, repetition is allowed. But in the edges, it is not allowed the repetition. The cycles, lastly, the repetition is not allowed except in the initial and terminal vertex, and in edges, repetition is not allowed.
We are done discussing what is the basic concept in the mathematics of graphs. We are also done discussing about graphs and universal. Now let's proceed to what is weighted graph. So in this section covers tree and spanning tree as introduction to weighted graphs and its application. First, let us discuss what is a tree. So, what is a tree? A tree is a mathematical structure that is a special kind of graph which has the following properties. First, it is let's have an example of a tree. What from the properties it is said that a tree is undirected and connected. Now, this is undirected because this vertex A, B, C, D, and E is undirected and connected because A, B, AEB is connected and has his own direction, which also the same as A, E, and D, which is also another direction, and as well as A, E, and C is also the same, which has another direction. And the last property of a tree is acyclic. Acyclic means there is only one root from any other vertex or has no cycle. This means that A, E, and D has only one root. We can draw it as like this. This is an acyclic because there is only one root, A, E, and B, as well as we can also draw A, E, and D like this, the same as the other vertices. Okay. Now let's proceed to forest. Forest is a disjoint union of trees, also called as a set of trees. So let's have this example. This is an example of a forest. As you can see, there are 4 trees. 1, 2, 3, and 4. As what is meant, a forest is a disjoint, means they are not connected. We have one forest here, we have also other forest here, and lastly this one. Next is spanning tree. A spanning tree of a graph is a subgraph. subgraph of which is a tree and contains all other vertices of the graph. Now let's have this example. This is an example of a graph. Now, it says that a spanning tree is a subgraph which is also a tree. Ang spanning tree kay subgraph. So, this graph can be, we can have 4 spanning tree of this graph, which is this one. T represents 3. Now, as what we can observe, that these trees was obtained from this graph G1. This one is this one, while the other one, this one, is we get it from here, as well as this one. Also, lastly, this one. Let's have this theorem 10.19 of Cayley's theorem, where there are v raised to the power of v minus 2 labeled trees with v is the vertices. Now let's have this example 2. It says, find the number of spanning trees of the complete graph K3. This one, this is K3, 1, 2, 3. Using Cayley's theorem, where V is equals to 3, there are V 3 vertices, 1, 2, 3. So given that we have K3, so which this is this one, and the formula of Cayley's theorem, V raised to the power of V minus 2. So let's distribute the number 3 to both V. So 3 raised to the power of 3 minus 2 equals 3 raised to the power of 1. So 3 raised to the power of 1 is equal to 3. Thus, there are 3 subtrees for complete graph K3. Graphically, figure 10.58 shows the 3 different subtrees, T1, this one, T2, and T3 of the graph. There are 3 known personalities who made a significant contribution in the field of graph theory, specifically on spanning tree, namely Robert Clay Prim, Joseph Bernard Kruskal, and Edgar W. Dijkstra. Robert Clay Prim developed Prim's algorithm in 1957, which is called a greedy algorithm that determines a minimum spanning tree for a connected, weighted, undirected graph. The algorithm finds a subset of the edges that forms a tree that includes every vertex where the total weight of all edges in the tree is minimized. The same algorithm was developed by Wojtek Jarnik, a Czech mathematician in 1930, and rediscovered by Edgar W. Dijkstra in 1959. The algorithm, sometimes called the DJP algorithm or Jarnik algorithm or Prim's Jarnik algorithm. Another proponent is Joseph Bernard Kruskal in 1928 to 2010. He's an American mathematician, statistician, computer scientist, and psychometrician. He introduced the Kruskal's algorithm for computing the minimal spanning tree or
what is called MST, of a weighted tree. The Kruskal's algorithm first orders the edges by weight and then proceeds through the ordered list, adding an edge to the partial MST, provided that adding the new edge does not create a cycle. Minimal spanning trees have applications to the construction and pricing of communication network. And last but not the least, Edsger W. Dijkstra, 1930 to 2002, a Dutch computer scientist, conceived the Dijkstra's algorithm in 1956, which was later published in 1959. The algorithm is a graph search algorithm that determines the single source shortest path problem for a graph producing a shortest path tree. Dijkstra's algorithm is frequently used in routing and as subroutine in other graph algorithms. It is a greedy algorithm and similar to Prim's algorithm. Dijkstra's algorithm starts at a source vertex and it grows a tree that spans all vertices reachable from shortest path weights from the source vertex.
This example, we have this shortest Hamiltonian circuit and we will find the value of each edges. For example, in this one, we have vertex A to B and B to C, C to D, D to E, and E to E. First, we will get the amount of vertex A to vertex B. In this, we have A to B is equals to 10 plus B to C, we have 8 plus C to D, we have C to D is 5 and D to E, we have 29 and E to A is equals to 12. And this goes, when we will add this all, it is equivalent to 64. Next, A to B, we have 10. B to D, we have 12. D to E, we have 29. E to C, we have 8. C to A, we have 20. This is equivalent to 79. And the last, C to B, we have 8. Plus B to A, we have 10. And A to D, we have 10. And C to B, B to A to D, D to C is 29, and C to E, and E to C equals to 8. And to find the shortest Hamiltonian circuit out of this figure, we will use the greedy algorithm to find the shortest Hamiltonian circuit. To find the shortest Hamiltonian circuit, we will use the greedy algorithm. We will start with the shortest edge, and on the vertex of each pick a not yet chosen vertex of the shortest edge. In this figure, we have D to C, E to A, B to D, and that we will find out what is the total of it all. We have here D to C, C to E, E to A to B, and B to D. We will find the value of D to C. D to C is equal to 5 plus E 8 plus A, we have 12 plus B, then plus D. D is 12. And that's a total of 47. Now we have our shortest Hamiltonian circuit, which is equivalent to 47. Out of this, shortest edge that has not yet chosen by our figure.
Now let's discuss what is weighted graph. A lot of problems can be presented using graphs with weights assigned to their edges. The weights could represent the distance between two locations, the travel time, the travel cost, and etc. It is important to note that the distance between vertices in a graph does not necessarily correspond to the weight of an edge. So let's have this example. Suppose that we have a map of a form shown in figure 10.64, which is the letters A, B, C, D, E, and X refers to towns that are connected by roads. If the length of these roads are as marked, what is the length of the shortest path from A to X? Here is the solution. The problem is find the shortest path from A to X. So let's have this D as X. So let's distribute the weight of each edges. 3, 5, 2, 5, 8, 7, 6, 4, 7. So it says that from path A, so let's start with A. So A to F has one value, so A to F. Next is F to X already. F to X, which has a value of 1 plus 6 equal to 7, which this is the shortest path or possible path from A to X.
So, hi everyone. We are going now to discuss about Euler's formula. So now we're going to discuss about Theorem 10.23. In Theorem 10.23, there are 3 rules. First rule is if the planar representation divides the plane into R or region, then we use B minus E plus R is equal to 2. Then second rule is if B is greater than or equal to 3, then E is lesser than or equal to 3B minus 6. So we use this in second rule of Theorem 10.23. And the third rule is So in rule number 3 is if B is greater than or equal to 3 and there are no cycles of length 3, then E is lesser than or equal to 2B minus 4. So we can use this. We can use theorem 10.23 to prove that a certain graphs are not planar. Notice if the cycle of a finite planar G contains at least edges, since edge occurs in exactly 2 faces or region, we have the inequality of KR lesser than or equal to 2E in a inequality. So now let's have an example. So we have a 3 examples to determine whether the following graphs are planar. So first example is the graph of the cube has the following vertices. It have 8 vertices, 12 edges, and 6 regions. So now we are going to use the rule 1 first. B minus E plus R is equal to 2. So now let's solve the rule number 1. So E minus 12 plus 6 is equal to 2. Then negative 4 plus 6 is equal to 2. So 2. Then now let's move to rule number 2. Rule number 2. Use the formula 3B minus 6 equal. So let's change the 3 multiplied by 8 minus 6 is equal to 24 minus 6 is equal to 18, greater than or equal to 12 equals E. Now let's move to rule number 3. Rule number 3. We use the formula 2B minus 4. 2B minus 4 more 16 minus 4 is equal to 12. Since all the rules satisfied, we can see that the cube is a planar. We can also verify from drawing a cube. We have graph number 1 and we have the graph number 2. It have an 8 vertices. 1, 2, 3, 4. Standard 1. So let's now draw. In graph number 2, we can draw like this. So, example 1 is a planar graph. Let's go. So, let's have some second example. Note that graph T5 and T33 are non-planar graph. So, the example is the graph K5 is a loop free and have a vertices of 5 and edge of 10. So, we're going to use the rule 1. B minus A plus R is equal to 2. So, 5 minus 10 plus R is equal to 2. So, the equivalent of R is 7. By the inequality, TR is lesser than or equal to 2E. Then move to para atong isolve 3 times 7 lesser than or equal to 2 times 10 equals to 3R lesser than or equal to 2E, which is a contradiction. Kay 3 is greater than 2, not lesser than or equal. So K5 is a non-planar. So we have to check the rule number 2. 3b minus 6 is equal to 3 times 5 minus 6 is equal to 15 minus 6. So equals 9 lesser than 10 equals to E. So since the solution contradicts theorem 10.23, number 2, rule number 2, E is lesser than or equal to 3b minus 6. So we can say that the graph K5 is a non-planar. Geometrically, these two graphs shows that K5 cannot be drawn in such a way that no two edges intersect. No. So now let's proceed to rule kanang example 3. So the graph T33 has a vertices of 6 and an edges of 9. So rule number 1, B minus E plus R is equal to 2. Then let's distribute the value. 6 minus 9 plus R is equal to 2. Then the R is equal to 5. By the inequality, TR lesser than or equal to 2E. Distribute 4 times 5 lesser than or equal to 2 times 9. Then 4R lesser than or equal to 2E, which is a contradiction. Kay 4 is greater than 2, not lesser than. So K33 is non-planar. So proceed sa rule number 2. 3b minus 6 equals 3 times 6 minus 6 is equal to 18. Okay, 3 times 6 is 18 man. So 18 minus 6 is equal to 2 greater than or equals to E. So proceed sa rule number 3. 2b minus 4 is equal to 2 times 6 minus 4 equals to 12 minus 4 is equal to 8 greater than E. Since we know that K33 is a non-planar, contradiction 2, E is greater than or equals to 2b minus 4. As I've reflected in graph number 2, note that the graph K3 cannot be drawn in such way that no edges will intersect. So, there are the graphs in example C. Now, let's have another example. Kung ganina is, ang atong gipangita is ang paghimo sa graph. Karon, ang graph na ihatag nato, then ato na lang i-prove nga ang kani nga graph is planar graph. So, gamiton to natong formula nga V minus E plus R is equal to 2. To prove nga ang kaning graph is a planar graph. So, kani siya, nani siya vertices nga 7. 1, 2, 3, 4, 5, 6, 7 vertices. And have an edges of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. And have a region of 5. 1, 2, 3, 4, and sa outer, this is pang 5. So, 5. So, distribute na to. So, 7 minus 10 plus 5 is equal to 2. So, 7 minus 10 is negative 3. So, plus 5 is equal to 2. So, ma-prove na to nga ang kaning graph is a linear graph. So, proceed ta sa laing example. Another example. So, before ta mo proceed sa laing example is mag-discuss ta sa lain nga kung sa Euler's formula. So, for Larry 10.7, if G is a plane graph with E times G connected to the components, then we use the formula B minus E plus R is equal to 1 plus E of G. So, next example is the graph sample 3. So now we can solve this graph. So B minus E plus R is equal to 1 plus E times G. So let's now count the vertices, edges, and the region of this graph. So vertices, we have 12 vertices and 13 edges, and have a region of 5. So now let's solve this graph. So 12 minus 13 plus 5 is equal to 1 plus C plus 3. Okay. Because 3 kay tulo man ikabok illustration nga itong nakita sa figure. So 12 minus 13 plus 5 is equal to 4. 1 plus 3 is 4 also. So thus B minus E plus R equals to 1 plus C D whole. So mao na ni atong whole about sa Euler's formula. Thank you for watching, and unta nakasabot mo sa akong i-discuss.
What a heartfelt momentum for us, our future mathematicians, because you will last long in our last topic, which is the graph coloring. A coloring for a graph is a coloring of the vertices in such a way that the vertices joined and edge have different colors. Of a graph is the least number of colors needed to make a coloring. Mao na siya'y chromatic number. Example, this diagram shows the minimum coloring of the Peterson graph. And what is the chromatic number? There are steps. For step 1, choose a vertex with highest degree and color it. So we have this highest degree of 4. Use the same color to color as many vertices as you can without coloring vertices joined by an edge of the same color. Step 2, choose a new color and repeat what you did in step 1 for vertices not already colored. So we color these other vertices. Step 3, repeat step 1 until all vertices are colored. So nahuman na nato siya colored tanan ang iyang vertices from the highest degree to the least. For example, we have this graph. In this graph, for step 1, choose a vertex with the highest degree and color it. Use the same color to color as many vertices as you can without coloring vertices joined by an edge of the same color. For this one, we have this chromatic degree number of 5, 3, 3, 3, 3, 3, and 3. We have this highest, which is the 5. This 5 is our highest, so we will color it. And then, also this 3, we will color it with orange. Step 2, choose a new color and repeat what you did in step 1. That's why we color the degree of 3. And then color the graph below and give its chromatic number. For this, we will color this degree of 3 over there, over here, here, and here. Because I choose new color and repeat what you did in step 1. And step 3, repeat step 1 until all vertices are colored. And we only have left 1, that's why we will color this only left 3 degree. And we have this graph coloring. In overall conclusion, if you experiment with different colorings, you will find its chromatic number is 3, as it appears to be in the graph here, in the graph. It is useful for the study of cell phone traffic, and especially the coloring maps, so that no two regions that share a boundary are the same color. I hope everyone that you will know everything about what we discussed, from basic concepts to graph coloring. Thank you so much for listening, and I hope that you will learn from us and you will apply it in our real life situations. Thank you so much.